All right, what's going on, Sam? All right, we'll wait on. All right, so today we're kind of in the home stretch with these olefinations, and we're going to talk today about a couple of methods. We're going to talk about uh, using triple bonds, like a hydroboration or triple bonds, and we're also going to talk about hydrozirconation if we get a chance to get to it. And that's really going to be uh, talk about with the olefinations, and we'll move on to another topic, hopefully on Wednesday. But if we don't finish this today, then we'll finish it on Wednesday. So hydroboration, and then hydrozirconation. And both of these processes are happening on alkynes. All right, and this is another way to synthesize olefins or double bonds. So let's jump in and deal with that. Uh, and so the reagents that we use for hydroboration, fix that. Sorry about that. Right, you'll see what we call catechol borane. Right, and this is so catechol borane is one reagent, and let me fix these oxygens right quick. One reagent that's used for hydroboration of alkynes, and then also, and it depends on the type of alkyne that you're working with. Also, thexoborane, right, and depending on uh, which type of alkyne you're working with, that's going to determine whether you use the catechol or the thexoborane. Come on, man. Why does it stop sharing? Sorry about that. All right. So with these hydrometallation strategies, right? You basically are going to be taking uh, an alkyne and treating it with either, again, a borane or a zirconium complex, and adding across the triple bond, right? So in this case, right, you take a triple bond and then you treat it with some type of organometallic or metalloid like boron, right? And then so you're adding to one side of that alkyne, and then the alkyne in turn is going to contribute electrons from the pi system, right? So you end up with a functionalized alkene, right? Where your metal or metalloid is now a part of that alkene. And using alkynes just precludes like rearrangement. If you use an alkene, there's too much potential for rearrangement. So we want to start with an alkyne, right? So you can take a borane, like catechol borane, and you can react it with an alkyne, a terminal alkyne. And the utility of the process is that if you use a terminal alkyne, then you can convert that into some type of uh, vinyl halide, which is, again, a great precursor to numerous other reactions, right? So if I take this terminal alkyne, I'm just going to put an R group here. Right, and I'm going to treat this with, and you'll see me abbreviate catechol borane like this, right? So catechol borane followed by bromine and sodium methoxide. Uh-oh, why is it not showing up? All right, it's up now. Can everybody see that? I'm not certain why um, there's this lag or why it's not showing up. Hold
I
up.
see it now.
It's just it's lagging for some reason. I'm not sure if it's not the Wi-Fi. All right, so that's that, and then this is your product. Okay, and let me show you that, and then we're gonna talk about how it happens. All right, so now this is, need to fix that because it happens with sin addition. All right, so you get a cis vinyl halide as the product, and again, it's important to be able to control the stereochemistry. Whether you get a cis vinyl halide or a trans vinyl halide, it's important to be able to control that stereochemistry, right? So the mechanism. Let's talk about the mechanism of the reaction, and the first step, obviously, when you add catechol borane, right? You're gonna generate a vinyl. Man, that lag is really irking me. Let me try to reshare this, because that is ridiculous. Come on, Zoom, tighten up. still lagging. Let me switch over. I'm gonna pause the recording too. I'm gonna switch over to my. All right. So again, with the if you want a trans vinyl halide, you can take that alkyne, treat it with catechol-borane, and then follow that up with iodine and sodium hydroxide. Uh, so if the synthetic application to this, let me show you that real quick. There's a compound FK506, which we'll talk about later when we talk about cuprates and organometallics. We're going to talk about that. But one of the fragments uh, with FK506 uses this technology to synthesize this a cis double bond, which is then a cis vinyl halide, which is then converted into some other species. So let me show you that right quick. So you have this. Right, so this is the desired product. Right? That's my desired product. And then so I can think about this in a couple of ways. I can think about addition from a retrosynthetic standpoint. I can think about this in terms of addition to this alkyne. Or I can think about addition to um, this already functionalized ring, right? Where I have a triple bond here that I can add to, right? And I can add all right, so you have a choice between and thinking retrosynthetically about this, like you have a choice between what you want to start with, right? But either one of these uh, start materials, both of them are feasible targets, right? If you start with the um, alkyne on the left, then you can potentially think about coupling that with this molecule right here, already functionalized with a thexoborane attached. Like so, right? So these two will couple, and that will give you your product. Or you could think about coupling this, let me fix that. The alkyne on the right, you could think about coupling that with a thexoborane like this. Right, where you could transfer this group. Yeah, you can transfer that ethyl group to your alkyne, right? Because there's a way to actually transfer the R group. If you take, let me show you that. If you take a thexoborane and use iodine and sodium hydroxide, so similar conditions to what we saw above. So if I take uh, so I could take the thexoborane and add some alkyl group onto it that I want to transfer to my alkyne. Uh, and instead of getting a vinyl iodide or vinyl halide, I'm able to actually get out uh, an alkene with a new substituent, right? So I can take um, this alkene or alkyne, sorry, and I could treat it with this borane where I have a with the thexyl group here, right? Right, and the final product will look like this, but I'm gonna show you how it happens too, because there's a, and I need to do this, and then I2 and sodium hydroxide, like so, right? All right. So if I take that, obviously I'm going to get to, and I'm not going to go through the whole mechanism. I want to get to the intermediate, which looks like this. And I'm gonna put a couple of arrows here, right? Because I'm not showing the I2 addition or the borane addition because we already know what that looks like, right? So I'm going here, right? So this is H, this is uh, B, and then I have my groups attached to boron, obviously that, and then plus the thexyl group, which doesn't transfer, by the way. Uh, and then
Dr. Rose is not showing up.
yeah, it's a lag again. Thank you for saying that because I'm just totally engrossed in writing. Let me reshare it. Good night, man. I need to start teaching this class first. I didn't have this problem at all earlier. I don't know what's going on. Maybe because it's later in the morning, more people are on the Wi-Fi or something. I don't know. Come on.
Probably on the server or something.
Yeah. Because I got AT&T Uverse and a lot of stay-at-home moms, and everybody's doing school at the same time too. So, and it's still frozen. Shucks, man. Come on. I think what I'm gonna start doing for this class is using my hotspot because that doesn't freeze ever. I tell you what, we'll pause here, because I don't want to keep having to go back and forth with this thing, and